So I'll give you a minute and then I'll give you a hint basically to get it started. Okay, so remember the first step of these is to break them down into like the detailed form of what the concentration unit means. So 35% by mass would be 35 grams of ethanol per 100 grams of the solution. But breaking that down even further, the bottom then would be 35 grams of ethanol and the difference, 65 grams of water, okay? And then you want to convert that to molality. So let's also redefine what molality is in more detail. That should be moles of ethanol per kilogram water, okay? So now you've got like a little bit more detailed information and you want to convert whatever it is you need from that detailed information into these units and then divide the moles by the kilograms to get your molality. So I'll give you a few more minutes to do that as well. You do not need the density here. They're giving you that in case you needed to go to molarity, but you're not doing molarity, you're doing molality, so. Okay, so top number gets converted to moles. Just the grams of water, because this is kilograms solvent. So you don't want the whole total solution, you just want the solvent. So 65 grams of water, convert that to kilograms, and then divide this by that, and you get 11.7 molal. So why do we have stuff like this? Well, okay, maybe not by mass, but like thinking about percent by volume would be a very normal way that normal people might communicate the amount of alcohol in water or in a solution. But they're not going to report it as molal, right? But our equations are all dependent on things like molarity and molality because we work in moles when we do chemical reactions and stuff, okay? So we have to end up doing a lot of these conversions as a result. So we're going to use that in a second. Let me explain first what we're doing, and then we'll come back and use the molality number in the further problems, okay? All right, so the concept stuff today is that the term colligative properties just means how something depends on the concentration of solute in there. So the three properties that we're talking about are freezing point and boiling point, and then osmotic pressure, okay? So freezing point and boiling point, you need to know that freezing point, so this is this equation, freezing points will drop with added solute. So if you add solute to a solution like salt to water, it's going to drop the freezing point. This is why we add salt to the roads when it's cold, so that ice won't form, because we drop the freezing point enough that it stays in the liquid phase. And the equation is going to tell us how many degrees the freezing point will change by. It doesn't tell us the new freezing point. So you have to know, for water at least, you have to know that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And then you will adjust the freezing point by this many degrees when you do a calculation. So if it comes out to be 2, that doesn't mean the freezing point is 2, right? Because that's higher than 0. That means you need to subtract 2 from the freezing point, because you need to know that freezing point always decreases. So it would be, the new freezing point would be -2, okay? And we'll talk about I a little later on, but M is the molality. So it's dependent on how much solute you have. If the molality is higher, you're going to get a bigger drop in the freezing point, okay? Every substance is going to have a constant associated with it. So we'll do ones for water today, but you'll have other examples that are different solvents. And there's one for the freezing point and one for the boiling point, okay? The boiling point is basically the same equation, different constant, but it still tells you the change in degrees. But for boiling point, the boiling point goes up. So boiling point increases with increasing solute. So if I have a pot of water on the stove and I'm gonna, I don't know, make pasta, and I add salt to it, that will actually increase the boiling point. So the temperature that the water boils at will now be like maybe 102 or 103 degrees rather than just 100 degrees. So in theory, that would cause things to cook faster. It's probably not going to be that noticeable, but okay, and then osmotic pressure is a very different type of property, but it is still dependent on how much solute you have. So I think most of you guys are either some sort of biology or maybe environmental science, which obviously both of those have cells in them, whether it's a plant or an animal. And osmotic pressure is probably something you've heard of because of that, because a cell membrane allows solvent like water to pass through it, but not a lot of the other stuff, right? So if you've got some sort of membrane where the solvent can pass through, and you have on one side, let's say, a solution that's not very concentrated, and then you have a solution over here that's very concentrated, what will happen is there will be a force, like a driving, a physical force, but also like a driving force, like a tendency for the solvent to move from one side to the other. So it's always going to move towards the more concentrated side. You're basically trying to equilibrate them. That's what's causing this, is that there is a drive for them to be equal on both sides. The thing that causes that to happen is what we call the osmotic pressure. It's weird because it is measured in atmospheres, almost like a gas pressure, but it's a pressure like a force, like, I'm applying a pressure to the chair, right? It's a force. So there's a force that's created when you have these unequal concentrations. And that's what this calculation is going to tell us, is like comparing it to a totally no solute versus one with solute. What is the force that's going to drive that solvent into the other system? So this one, again, we'll talk about I in a second. This one is molarity, though, not molality. And the R is actually the gas constant. So it's in your exam equation sheet. There's two of them, though. It's the 0.08, not the 8.3, okay? So make sure to do enough examples that you make sure you do that correctly. But 0.08 to 1, I think. And then the temperature is in Kelvin. So it's like all the same units as the gas law. So the same concept from the gas law, Kelvin, molarity, and you get it in atmospheres. Okay, so we'll do some of those as well. So we're going to go ahead and start with this one. And we already calculated the molality, so we can go ahead and use the equation from above to calculate a new freezing point for this solution. So the change in temperature of the freezing point is going to be equal to I molality times the constant. Now, I for a covalent compound is just 1. And it probably won't make sense why until we talk about ionic compounds. So for now, just plug a 1 in there for the I, and then we'll talk about ionic compounds in a second. Okay, so go ahead and calculate. I want you to actually calculate what the new freezing point is using this concentration up here and your constant and an I of 1. Since this was 35%, just 2 sig figs, I'm going to include 2 sig figs. Okay, so that means that this solution, and this is like 80 proof, because someone had to look it up, or tell me. No, they didn't have to look it up, they knew. They said it's percent by volume times 2. So percent by mass, I calculated that, and it's like about 40% by volume. So that would be 80 proof. So it would not freeze until negative 22. This is why you could stick, you know, a bottle of, at least if it's hard liquor, into the freezer and it doesn't generally freeze. Okay, so now go ahead and do the same thing, but now for the boiling point. And you'll notice the constant for the boiling point is a lot smaller, so 1.86.5. So that just tells us that the effect on boiling point is a lot less dramatic than the effect on freezing point. So it's not going to drop, well, the change is not going to be nearly as much for boiling point. Okay, so you should get 106 degrees Celsius. Again, when you get that 6, that's not the new one. You have to add that to the existing boiling point, okay? So you better make sure you remember, boiling point goes up, freezing point goes down, because that's not embedded in the equation. If it was something other than water, like they're always going to give you the constants. If it's something other than water, we'll give you the freezing point or the boiling point. But obviously I expect you to know water's freezing point and boiling point. Okay, it only gets a little bit more complicated with ionic, but not too bad. So when ethanol or any covalent compound dissolves into water, it stays as its molecule. So ethanol doesn't break up into like carbons and hydrogens and oxygens. It stays as C2H5OH. C2H5OH. Okay, so it breaks into its molecules. Like the molecules aren't near each other, but then the water just surrounds each individual molecule. Okay, so if I have 100 units of ethanol, 100 molecules, I'll get 100 little ethanol molecules in the water, and they'll all get surrounded by the water. If I had something like sodium chloride, though, when sodium chloride goes into water, it breaks up into sodium plus and Cl minus, and then those all get surrounded by water. Okay, so if I had 100 sodium chloride units, I'd actually end up with 200 individual little things in the water. Okay, and the number of things is what affects that change in boiling point or freezing point. And so the I is what accounts for that. So when ethanol dissolves, it starts as one thing and it goes to make one thing per total number that you started with. So if you have 100, you still have 100. With sodium chloride, for every one thing, it makes two things. So when you do this calculation, you need to write 2 in the I to account for the fact that you're almost like doubling the effectiveness. Not almost, you are. Like if you put the same number of moles of ethanol in one thing of water, and you put the same number of moles of sodium chloride in another thing of water, you're actually going to get twice as much of a drop. So like the sodium chloride, you would get negative 44 Celsius, not 22, okay? So that's what the I accounts for. So just to like practice this a little bit, skip this slide and go down to this next one. We're just going to look at this top problem, and I'm going to add one more on here too. And it's less about the question itself and more just about making sure you guys know how to count the I's. This question asks about per kilogram. Let's just say per mole. So it says, if each of these costs the same amount per mole, which one would be most cost effective as a way to lower the freezing point of water? So like, what should we throw on the streets in order to get the ice to melt, assuming that they all cost the same? Now, obviously there's things like safety and like, is it going to mess up the concrete or whatever? But all other things being equal, which one would be the most effective? So we want to look at the I, because the change in freezing point is only dependent on how much stuff there is, so how many moles, and then how many things does it break into. So like this compound, all nonmetals, that's covalent, so the I would be equal to 1. For sodium chloride and potassium chloride, each of those would be equal to 2. They just break up into those individual ions. And maybe let's talk about the one above as well that's in the previous problem. It's KNO3. It's just important to pull in some polyatomic ions so you guys don't forget how those behave. So NO3 minus stays as NO3 minus, okay? When you have potassium nitrate, this is going to separate into K plus and NO3 minus, not N and O and K, but just 2 ions. So that one would also have an I of 2. Strontium chloride and magnesium chloride, those are going to break into SR. I don't care if you don't remember the charges, but SR2 plus, Cl minus, and Cl minus. Cl2 is not a polyatomic ion. It's saying you have 2 chlorine ions, okay? So 3 different things there, so the I is 3. The only time I think you might get confused by this is the polyatomic ions. So the way to like account for that is any time you see a polyatomic ion, just put the parentheses around it, even if you don't really need them. Like KNO3, write it with parentheses around the NO3, and that will remind you that thing stays together, okay? So magnesium chloride is also going to be 3. And then calcium phosphate would be 3 calciums and 2 phosphates, so 5. Thanks. So that one would be the most effective at reducing the freezing point. Because if I add 1 mole of each of these things, this one's going to be 5 times more effective than that one is. Okay, so now we have enough information, we can go do this problem. And in this one, so if you remember on Friday, we did 3 different types of problems. We did calculate a particular concentration unit. So like you're given information and it says calculate the mole fraction, right? Or you're given a concentration unit and you have to convert it into another concentration unit, which we practiced at the beginning of class. Or the last thing is you're given a concentration unit and you have to use it as a conversion factor. So that's what this one is going to practice. You're still going to use one of these equations we've been doing with the freezing point. But then the end part of the problem is going to incorporate this using the molality as a conversion factor. Okay? So start with your freezing point equation. Figure out what it is you're solving for, what do you not have, and then use, I'm just telling you basically, you're solving for the molality in this case, okay? You don't have the molality, you're going to solve for that. And then you're going to use the molality as a conversion factor to do the part in pink. Okay, so I'm going to give you a few minutes. I'll do the thing I always do, or I'll do the first part in a couple minutes, and you can check your work. Oh, important piece of information. If you haven't already been told this in lab, the density of water is 1 gram per mil. It varies slightly with temperature, but in an instance like this, they really should have told you that the density is 1 gram per mil, but just assume it. If you think you need it and it's not given, you can just assume it. So you can assume that this is 275 grams of water. So I've also now, in addition to finding the molality and breaking it down into its two components so that I can use it, as a conversion factor, I've also planned out my calculation. So I had to start with that 275. There's nowhere else to start. And I'm trying to find grams of KNO3. So knowing that I can use the molality, I can go from grams to kilograms, then use that conversion factor, then go from moles to grams of KNO3. So this should start feeling like the whole year is kind of coming together in these types of things. You're now using, dimensional analysis stuff that we learned probably September, October to do these calculations. Okay, so half the battle with this stuff is just figuring out what is it asking, what units do I need to have it in. It's not that these equations are hard. Obviously, it's like 3-part equations. It's just kind of adding into all of these same types of things that we've been doing, like I said, since September. So when you look at a problem like this, like the one that we just did, start by figuring out what is the end unit of the thing I'm looking for, grams of KNO3. And then what information do I have? I have a volume of water or a mass of water. I have a temperature. I have a constant. And like pretty quickly, you're going to see that you don't have enough information to get the molality. You need to find the molality, and you have all the other stuff. So usually if you can just isolate, what do I have to start with, and what is the thing I'm trying to get to, you'll probably be able to plan out your calculation fairly clearly. But it's that same thing we've been saying, since last semester. Okay, so the last two we're going to do are osmotic pressure. So I'm going to skip over a couple of these just because there's a lot of them. I guess it was just that one I skipped over. So we're going to go ahead and do this one. And I'm going to give you guys, since I explained the equation and we have the time, I'm going to go ahead and let you guys take some time to do this one on your own, because I don't think I need to explain it too much. Just remember to use the correct R value. And if you don't remember where this is, look it up on your exam equation sheet so you're familiar with which one it is and where it is. And these are the units of the things that you're, the constant, and then the units for the other stuff, okay? So I'll go ahead and give you a few minutes to work on that one. don't forget this is molarity, not molality. Okay, so check your answer when you finish. If you're off, double check your molarity. Make sure that's right. You need to be in Kelvin, so 298. So what this pressure is telling you is the salt solution here. So this is literally a salt solution. How that compares to just plain water. So if you had, like, your cells don't have plain water in them, so this pressure isn't this high between blood and your cell. But if you had plain water compared to this saline solution, that would be the driving force that would be pushing the water to basically move in and dilute that salt solution. But usually they're much closer in comparison. So there's another equation we use to compare when you have two different ones that are of differing concentration to describe that pressure. Okay, we'll do another one of those. I like this one because it's a good plant one. I'm a plant person. So osmotic pressure required for transporting water to the top of a large tree, 20 atmospheres, okay? So it's pretty significant pressure. So they want to know in that case, what's the concentration of the tree sap? Now sap is basically sugar, so that means the I is 1 because it's a covalent compound. So go ahead and calculate the molar concentration that sugar solution would have to be in order to transport this up to the top of the tree. There must be another purpose of sap, but I bet you that is probably one of its primary purposes, because you're talking about high concentrations, so the water gets pulled in to, dilute that sap. It's very interesting. And if you finish, maybe just so I don't rush people along, but if you do finish, why don't you go ahead and do the next one? I think there was just one of them that we didn't get to. So homework is due tomorrow night for chapter 14. This is the end of it. And then prep for chapter 16. I love chapter 16, so just be prepared. It's very fun. That's it. And I'll see you guys on Wednesday.
But make sure you put it in 1.25 speed. While it's not on screen, they can't see it. They can't see that. Just do it ahead of time. Got it. No, guys, I'm just gonna our activity. It's not. Well, I mean, one of them is like write it down for yourself. You know, you're not to leave or mentality, but it's literally just for you. Well, what's your theme again? Growth mindset and embrace.